Welcome to Lecture 14, Nuclear Chemistry. In this lecture, we'll introduce nuclear notation, talk about the types of radiation, describe nuclear energy and uses of radioisotopes, and introduce the concept of transmutation. First off, nuclear notation. This is just the standard form of writing an element symbol, but by writing the mass number on top here, we're going to be able to keep track of what isotope we're talking about. Because the atomic number is implied by the symbol, it's often omitted. So often you'll see something like this, 239 plutonium or plutonium-239. Now, radioactivity. Some nuclei are unstable. These nuclei decay to form new nuclei, and the decay emits particles or energy. There are three primary types of radioactivity. The first type is alpha decay, and that alpha decay is actually a helium nucleus, which is usually denoted as 4He or 4 and this alpha symbol. And alpha decay is usually seen in nuclei that are too large or that have too many neutrons. We have two different types of beta decay. There's negative and positive beta decay. In negative decay, an electron is emitted from a nucleus. That is to say, a neutron is turned into a proton and an electron. And this is why we see this in elements that have too many neutrons. In positive beta decay, also called positron decay, this happens in an element that is small but has too many protons, and that proton is converted into a neutron and a positron. And finally, gamma radiation, which is just high energy light. These are oftentimes emitted from nuclei that are just in an unstable configuration. The mass isn't going to change here, the charge isn't going to change here. But as the nucleus settles down from a high energy state to a low energy state, gamma radiation can be emitted. So here are some examples. Previously we mentioned the plutonium-239. Here it is decaying into uranium-235 and an alpha particle. This is alpha emission. And then here we have nitrogen-17. It's undergoing negative beta decay to form oxygen-17 and a beta particle, a negative beta particle, which is just an electron. Here is an example of magnesium-20. This one has got too many protons, so it's going to convert one of those protons into a neutron and emit a positron, which is a positive beta particle. And here's technetium-99 metastable, which is to say it's going to decay into 99 technetium, which is just a different configuration of the protons and neutrons in the nucleus. And in so doing, it loses energy. And that energy comes out in the form of a high energy gamma photon. Notice the sum of the mass numbers on the left and the right are always equal. And we can check that here. 239 plutonium, 235 plus 4, 239. 17, 17, and 0. Still works. The sum of the atomic numbers also always equal. So for plutonium, I haven't written it here, but plutonium is element number 94, uranium is 92, and helium is 2, and 2 and 92 is 94. 7, 8, and negative 1, it works here too. Both of these are just restatements of the law of conservation of mass and the law of conservation of charge, which state that the mass and the charge cannot be created or destroyed. Now, in many cases, the product of radioactive decay is itself a radioactive element. So we get this long chain called the decay chain. That's the pathway that the parent isotope takes through all of the daughter nuclides until it gets to the stable nucleus. So here's an example. This is radioactive thorium-232. Here it is decaying by alpha emission to form radium-228, which is unstable. It undergoes negative beta decay to form 228 actinium, which in turn undergoes beta decay again to form 228 thorium. Still radioactive, undergoes an alpha decay to form 224 radium, which is itself radioactive, forms helium again in an alpha decay, and 220 radon. Another alpha decay to 216 polonium, and another alpha decay to 212 lead. 212 lead undergoes beta decay to 212 bismuth, which in turn undergoes beta decay to 212 polonium, which again undergoes alpha decay to form 208 lead. But 208 lead is non-radioactive. So you get this long chain from 232 thorium through a whole host of intermediates all the way down to non-radioactive lead-208. Now, some radioactive nuclides can be split by being struck by a neutron. Probably most famous of these is uranium-235. If you hit it with a neutron, you form uranium-236. That uranium-236 is very unstable, and it decays via a different process called spontaneous fission. Fission just means to split, And in the case of uranium-236, it can split into a number of different daughter isotopes here, but probably the most common is an isotope of barium, an isotope of krypton, additional neutrons, and a whole bunch of energy, both kinetic energy in the form of these daughter nuclides that are very energetic, have got a lot of kinetic energy, but also gamma radiation. The neutrons that are emitted, these three neutrons, can split more uranium-235. If you get this going real quick, it's called a nuclear chain reaction. If the nuclear chain reaction happens very quickly, this is an atomic bomb. If you slow it down somewhat, you get a modern nuclear fission reactor. If you want to slow it down, you're going to need something to absorb some of those neutrons. You don't want all of them spitting out because you're spitting out more neutrons than you need. So you need a neutron absorber, and you also need something to slow the neutrons down so that not all of them cause fission. So you also need a moderator. The moderator in modern nuclear reactors is typically water, and the neutron absorbers, these are called the control rods, and these are sometimes made of beryllium or other elements of boron that are good at absorbing neutrons. The amount of energy that's given off here is hard to overstate. It is absolutely enormous. The amount of energy that can be harvested from 1 kilogram of uranium-235, now understand that's 2.2 pounds, you can hold it comfortably in your hand, is the equivalent of the energy you would get by burning 2.7 million kilograms, over 5 million pounds of coal. The entire state of West Virginia only produced about 100 million kilograms of coal in the year 2015. That's the equivalent of 37 kilograms of uranium, which is only 82 pounds. So you could probably pick that up, although I wouldn't advise it because it's pretty radioactive and you want to avoid exposure. Still, it's amazing that the energy contained in a year's worth of coal mining could be picked up by a single person. This is why nuclear fission is so valuable and so efficient as an energy source. To put this another way, we have a number of nuclear aircraft carriers. These aircraft carriers typically have a prescribed lifespan of about 50 years. We figure they're going to be in the water for about half a century. During that time, they only are ever refueled once. They're typically fueled with uranium-235 at the beginning of their operation and then again about 25 years later, which is just astronomical to think that this boat could operate for 25 years and never be refueled. Now, we previously described the use of radioactivity as a way to date items way back in our lecture about half-life. Radioactive elements are also used to treat cancer. One example of this is thyroid cancer. Your thyroid gland absorbs iodine in your diet to form a hormone called thyroxine. Thyroid cancer can be treated by giving the patient radioactive iodine atoms. Those iodine atoms are concentrated in the thyroid gland, and then as they decay, they emit particles which kill the surrounding cells. This tends to kill more cancer cells than not, and as a result, this is a good way to kill thyroid cancer. Transmutation. We can do this process in reverse. Rather than letting a radioactive nucleus spit out an alpha or beta particle, we can hit particles with alpha or beta particles and make new elements. And this process is called transmutation. Here's an example here. Iridium-193 being hit with an alpha particle can make gold-197. And that's right, you really can make gold from another element, but it's not a chemical process, it's a nuclear one. Unfortunately, this is not a good way to make common elements. And the reason is that, one, the products tend to be radioactive, which is not great. And two, you're only making them an atom at a time, which is really, really slow. So even for super valuable elements like gold and platinum, this simply isn't a good way to make them. However, it is a decent way to make special isotopes of those elements. And we're going to talk about another one of those in just a second here. This is really the only way to synthesize transuranium elements. Elements higher than atomic number 92 aren't really found on Earth. So if you want to synthesize them to study them, you have to make them in the lab. And here's an example of a Japanese team synthesized element number 113, nihonium. And here's how they did it. They took neptunium-237, and they hit it with calcium nuclei and to form this nihonium-285. Okay, and this is how all of those new elements that have been recently added to the periodic table, this is how all of them were synthesized. Now, important side note here, this calcium-48, this is not a particularly common element naturally, and this one can also be synthesized via transmutation. In the case of nihonium, I can't stress enough that this is not a good way to make a lot of this substance. So far, scientists have only managed to make less than a dozen atoms of nihonium, which is an incredibly small amount. But even from that tiny, tiny sample, we've been able to determine some of the properties of this very heavy element.